So next I'm going to discuss about fully developed flow. See, we need to understand what is meant by this fully developed flow in a proper manner. It is a very interesting topic. Okay, so just listen properly. Let me take a pipe. Okay, let me take a pipe like this. Okay, right. A pipe's diameter. Let the pipe diameter be this. Okay, so I'm just representing the pipe. If you want, I will represent like this. So this is a pipe. Okay, so a fluid which is initially flowing with a velocity, let me take that velocity be u. Okay, or it is, let me take it as u infinity. Okay, let the velocity be u infinity, which is flowing initially. Okay, once the fluid enters the pipe, okay, once this fluid enters the pipe, what will happen? This is pretty much directing, which we know already, right? So this is a pipe, a three-dimensional pipe, right? So it will be having a surface like this. It will be having a surface like this. You just have to imagine there is a pipe. Its surface is present everywhere. Once a real fluid, just take that it is a real fluid. So we are going to discuss about the fluid which is real, which means a fluid which is having viscosity. So a real fluid entering in this. Okay, so there is a top surface, there is a bottom surface, there is like this is a complete surface, right? A circular surface, it's a pipe surface, a cylindrical surface. So everywhere it is a solid, and this is a fluid. Once fluid flows inside solid, okay, one fluid flows inside solid, or one fluid directly becomes in contact with the solid, what will happen? Just you need to recollect something from your first chapter, that is no slip condition. So when we are discussing viscosity, I said what is meant by no slip condition. Once this fluid flows inside, there is a surface of a solid, and that solid is going to, like, the interface of fluid and solid will reach zero velocity, right? Or I can say that the relative velocity between solid and fluid at the interface is zero. So let me take a section like this. Okay, let me take a section like this. Here the velocity is going to become zero. Here the velocity is going to become zero. We know this pretty much clear, right? And I'm just drawing top and bottom, but in fact it is three-dimensional. You need to imagine this. It is a three-dimensional, right? So it's a three-dimensional, and the velocity profile which I'm going to get, that will also be three-dimensional. This we discussed already. If there was a solid surface, the fluid flows over it, it will reach zero velocity, and there will be development of velocity profile. So there is going to be a development of velocity profile everywhere around the surface. It is not only in top and bottom, around the surface everywhere, and it will reach a constant velocity. It will reach a constant velocity after some distance. Okay, after some distance it will reach a constant velocity. Okay, right. So just consider that it's a constant velocity everywhere. There was a velocity profile until this distance. Let me take this distance is x. Okay, so top is also x and bottom is also x. In fact, it is not top and bottom, everywhere from the surface. So from the surface there will be development of velocity profile. Imagine it. Otherwise it's very difficult to observe this properly. Okay, so let me take this is the center of the pipe. Okay, now let this constant velocity, right? So let this constant velocity be v. Okay, or else this is u infinity, right? So let me take this constant velocity be u1. Okay, right. Now my question is, try to pause the video and answer the question. Okay, so what is my question? Will this velocity u1, okay, will this velocity u1, will it be equal to u infinity? Okay, so u infinity is nothing but free stream velocity. Okay, free stream velocity means velocity of the fluid before getting into contact with any solid. I guess I already said this when I was discussing first chapter. So velocity of the fluid before getting into contact with any solid surface. Okay, so that is free stream velocity, right? So this free stream velocity is u infinity, right? So my question is, will u1, that is this constant velocity, after some distance, it is reaching a constant velocity. Okay, it is reaching a constant velocity. will this constant velocity, will it be equal to infinity, or will it be less than u infinity, or will it be greater than u infinity? Which one out of these three is correct? Just pause the video and try to answer it. Right, listen. So now I hope already you would have what I can say, already you would have answered one, right? So either one, that is u1 is equal to infinity, or u1 is less than u infinity, or u1 is greater than u infinity. So out of these three options, everyone would have selected one option, right? So most of them, okay, most of them, I'm not saying that everyone, but maximum percentage of students, like though maximum percentage of the students would have selected option 1 only, which means this velocity u1 equals to velocity u infinity. So that is what most of them would have answered, right? So I believe that because most of the times in classroom also I will get the same answer, that is u1 is equal to u infinity, but it is not correct. So this option 1 is completely wrong. I will prove you. Okay, so let me prove that. See, I will take, like, this cross sectional area is A, right? Let me take the cross section area is A. So this is the cross section area, just considering the cross sectional area A. Okay, right. If initially when the fluid enters, okay, when the fluid is entering the pipe, it is entering, just I will show you. Initially when the fluid is entering, it is entering everywhere, okay, everywhere it is having same velocity, okay, it is having same velocity u infinity, u infinity, u infinity only, okay, everywhere it is having same velocity. In general, we know one formula for finding mass flow rate, right? So mass flow rate is nothing but rho A into V, density into area into velocity. Now mass flow rate at the inlet, okay, when it is entering, okay, before starting to flow inside, when it is entering, mass flow rate is nothing but rho, this total cross section, everywhere, at each and every point, the velocity remains u infinity only. So rho A into u infinity, this is mass flow rate at the inlet. And the mass flow rate which is entering, okay, see, this is the mass flow rate, rho A into u infinity is the mass flow rate at which it is entering this section, okay, at which it is entering this section. Now if I want to find mass flow rate here, okay, mass flow rate here at this section, just think about it, what will happen? It is similar, rho A is fine, but is the velocity same everywhere? See, this is my cross section, just consider there is a cross section here at OO, there is a cross section at OO, not OO, there is a cross section here. If I take this section as my first section, okay, in the first section there is a cross section, right, and that cross section area is equal to A, but here in that cross section area the velocity is not distributed same everywhere, that is at each and every point, velocities are not same. In fact, near the surface, okay, if you consider near the surface of the circular pipe, there was development of velocity profile. Okay, let me just draw that. Okay, so this is what I got over the complete area. Okay, so when it is entering, velocity remains same over the total area, so m inlet is equal to rho A u infinity. But when it is present at the section 1, velocities are not same, there was some variation in velocity. Let me consider the answer u1 is equal to u infinity. If u1 is equal to u infinity, right, so this, if u1 is equal to u infinity, let me take u1 is equal to u infinity. If u1 is equal to u infinity, then over this, that is over this complete area, like what I can say, that mass flow rate will be same because it is rho A into u infinity only. So over this area the velocity is still same, so mass flow rate is same. But if you consider top and bottom, you just consider this and consider this much amount of velocity has been lost. this much amount of velocity has been lost. If I am losing this much amount of velocity, listen carefully, here over this section my velocity remains same everywhere, over this section my velocity remains same everywhere, so like velocity remains same everywhere, but here this much amount of velocity in top and bottom has been lost. If this much amount of velocity has been lost, then the mass flow rate is also going to decrease until if I take u1 as u infinity. If u1 is equal to u infinity, then surely mass flow rate corresponding to this velocity profile will be less. I hope you understood. If u infinity remains same everywhere, I am getting this is the mass flow rate, for example 10 kg per second. Okay, so 10 kg per second is the mass flow rate. If u infinity, for example, u infinity is 10 meter per second. Okay, u infinity 10 meter per second acting over the complete area. But now only over this area 10 meter per second. But from here to here, velocity is varying from 0 to 10. From here to here, velocity is varying from 0 to 10, which means the velocity from here to here, the mass flow rate from here to here, is decreased. It is decreasing. Okay, clearly, you could see if I draw a line like this, this much amount of mass I am going to lose there. If this u1 is equal to u infinity, but you know that the mass entering, it is entering at 10 kg per second, and this pipe is completely confined. Pipe is completely confined means there is no way for a fluid to escape. If 10 kg is entering, then this section, like in this section also only 10 kg should pass. If 20 kg is entering, then this section also only 20 kg should pass, because there is no possibility for fluid to escape up, or there is no possibility for fluid to escape down. If 10 kg enters, in this section also only 10 kg, in this section also only 10 kg, which means mass flow rate here and mass flow rate here should be same. So the mass flow rate should be same, but if it has to be same, then u1 cannot be equal to u infinity. The reason, as I explained, if u1 is equal to infinity, then there was a reduction in mass. This much amount of velocity is reducing, which means that much amount of corresponding mass is also going to reduce. Okay, this is not applicable for an external flow. Since it is an internal flow, there is no possibility for a fluid to escape upside or escape downside. So if 10 kg enters here, the same 10 kg should pass through this. The same 10 kg should pass through this also. Okay, so then now you could have already guessed it, right? So u1 cannot be equal to u infinity. U1 can never be equal to u infinity. If u1 equals to u infinity, then mass conservation is not getting satisfied. Inlet mass and mass at any sections are not going to become equal, but inlet mass and mass at any section should be equal. It has to be equal, right? So as it clearly says, it has to be equal. If I am taking same velocity, then this much amount of mass is getting lost, right? Now if it is not going to be same, then u1 should be greater than u infinity or less than u infinity. It's pretty much clear, right? So u1 has to be greater, because see, this much amount of mass we are losing. If I am losing this much amount of mass, that mass has to be compensated. That mass has to be compensated by increasing this velocity. Okay, so instead of keeping a same velocity, it's very simple. Here velocities are decreasing. Okay, here velocities are decreasing, here velocities are decreasing, and that velocities are getting compensated here. So here velocity will increase. By increasing this velocity, here velocities are decreased, here velocities are decreased. So this velocity is increasing. By increasing this velocity, the mass flow rate is getting compensated. So if it is entering at 10 kg per second, then this section will also be 10 kg per second. This section, any section I take, it will be 10 kg per second. So I hope you understood it very clearly. So what is the statement which I was supposed to give? This u1, this constant velocity u1 has to be greater than that of u infinity. It's a very good conceptual thing. If you understood it, then it's very good. Even if you not understood also, it is not very much useful for problem solving, but still it's a very good concept. Try to go back to the video and see it again, it will be more clear for you. Okay, so let us proceed further. See, the fluid flows further, this layer of the fluid, okay, this layer of the fluid, this fluid particle, as it is moving further, it is in contact with the fluid which is at rest, right? As it is moving further, this fluid particle is going to retard more. In general, this fluid particle which is at rest is retarding this. Because of that only I am forming a velocity profile. And this fluid particle is retarding this fluid particle is retarding this. And as I am moving from this point to this point, this fluid particle was in contact with this fluid particle at rest for more time. Since they are in contact with this fluid particle at rest for more time, this is going to retard further, okay, which means this velocity will decrease. Similarly, this velocity will decrease, similarly this velocity will decrease, similarly this velocity will decrease. Because of decrease in those velocities, the distance, this distance to reach a constant velocity will increase. Let me repeat it. As I am moving forward, this fluid particle was in contact, that is there will be coercive force between these two fluid particles, as this fluid particle was in contact with the fluid particle which is in rest for more time. As I am moving from here to here, it is in contact with the rest fluid particle for more time. If it is in contact with the rest fluid particle for more time, this is going to get retarded further. Similarly, this is in contact with this, right? So if the second fluid particle retarded further, then the third will also be retarded further, then fourth will also be retarded further. Similarly, this will also be retarded further, then this will also be retarded further. Because of that, for reaching a constant velocity, that is for reaching a constant velocity, it takes more distance. Okay, so let me draw that. See, this is x, right? So it is not going to reach there. So this is what? Similarly, right, so now you could see I am not drawing it properly, but this has to exactly, this is the center of the pipe, so it has to exactly pass through the center. The upside and lower side should be exactly symmetric. Okay, so this distance, let me take it as x dash, and this distance, let me take it as x dash, and let me take this is u2. Okay, now answer my question. One thing is pretty much clear. As the fluid particle retarding further, this distance is increasing, that is the distance taken for reaching a constant velocity is increasing, right? What will happen to this u2? That is my question. Will u2 be greater than u1 or will it be less than u1? See, it's pretty much clear, right? It has to be greater than u1. Why? Because we are losing further amount of mass here. Since the velocity profile is getting extended, I am losing more amount of mass here. So here I am losing more amount of mass. For compensating that, this velocity should increase, which clearly states u2 is greater than u1 and x dash is greater than x. Okay. So as we are moving further, as I am moving further at one particular point, let me draw it, at one particular point, that velocity will exactly reach the center, velocity profile will exactly reach the center. Similarly, velocity profile will exactly reach the center. Once we reach this point, okay, once we reach this point, that is the velocity profile will exit until center. Similarly, velocity profile will exist until center. Until I reach this point, okay, until I reach this point, velocity profiles will be continuously changing. Velocity profiles are not same. See here different velocity profile, here different velocity profile. Let me erase it. Until I reach this point, velocity profiles are continuously changing, right? So here x is increasing and u1 is increasing, right? And for reaching this constant velocity, the distance taken was continuously increasing, and finally this distance x1 is reaching the radius itself, radius of that particular pipe itself. See, if I join, from the starting point, we'll use another color. If I join all the points, okay, at which the velocity is reaching constant. If I join all the points at which the velocity is reaching constant, okay, so this, Similarly, okay, this, if I join all the points at which the velocity is reaching constant. Now if you see above this, I just drawn a line, right? So above this line the velocities are constant. So here velocity is u1. Similarly here velocities are u2, which means this fluid is behaving like an ideal fluid, even though it is a real fluid, but the flow which is happening was something like ideal fluid flow. What does actually it means? Ideal fluid flow means there is no viscous effect, right? Here there is no viscous effect between the layers. So even though it is a real fluid, now the flow between each layers, it is like there is no viscous effect between each layers, and which means it is behaving like an ideal fluid flow. So I can say that these are going to be like these straight, as I am getting everywhere velocity remains same. So this I can say that it is irrotational flow. Why it is irrotational flow? Just think about it properly. Since it is an ideal fluid flow, okay, so if it has to be, since the velocities are same, okay, there is no possibility for rotation here. Okay, since it is going to be an ideal fluid flow, even though if it is a real fluid, okay, but the velocities are constant everywhere, so it is irrotational. But if you see here, velocities are varying, which is behaving like a viscous fluid. It is a viscous fluid and there was a viscosity, so here the flow will be rotational. Okay, right. So now you could see this layer, above this layer velocities are constant, below this layer there was a velocity profile, and this layer, okay, this blue color line from this point until this point, and similarly this point until this point is called as boundary layer. A boundary layer of a boundary layer inside a pipe. Okay, so we will discuss about this boundary layer in deep later, but for now you need to understand this is boundary layer of a pipe. So how we are getting boundary layer inside a pipe, okay. And now what is the maximum boundary layer thickness possible? See this distance, okay, this distance from zero velocity until the boundary layer, from this distance until boundary layer, that is boundary layer thickness. In case of a flow through a pipe, okay, flow inside a pipe, what is the maximum boundary layer thickness possible? Pretty much clear, right? So it is radius. So this radius, after this radius there is no possibility for development of boundary layer, but from this point to this point boundary layer is continuously increasing, and once it reaches here boundary layer is constant everywhere. The thickness was r only. So initially x dash, it is reaching r, and after that it is constant. So boundary layer thickness remains constant, and the maximum value of boundary layer thickness in a pipe flow is r. So these are some 1 mark questions, okay, right. So regarding this irrotational and rotational also we will talk more once we enter into boundary layer chapter itself. But now why I introduced this concept is to differentiate between two types of flow. The first one is developing flow, or it is also called as entrance region, or it is also called as developing region. Okay, so the region or the flow until which the velocity profile will be developing continuously. So there are some proper definitions, I will give that, but for now you understood like this. So velocity profile is completely developing, and after this point, okay, this velocity profile will remain same everywhere. Okay, so that is fully developed flow. So once I reach this point, after that the velocity profile will remain same, so that is fully developed flow, right. So I will give you the proper definition, like I will erase it and I will draw it again, and I will give you the proper condition for developed flow and developing flow and fully developed flow. So let me just frame that fully developed flow properly, okay, right. So we know that in a developing flow or a entrance region there will be development of velocity profile, and at one particular point velocity profile will be fully developed, right. So what is the conditions for fully developed flow? So first condition is, let me write it here. The first condition fully developed flow is u, that is the velocity profile is not a function of x. Velocity profile depends only on r. What actually it means? You could clearly see, but see, I didn't draw it properly, but let me explain it properly. Listen. See, velocity can vary radially. If I increase the radius, so here radius is 0. As I am continuously increasing, radius is varying from 0 to r. So as I am increasing the radius, velocity profile can vary. Okay, velocity profile will vary radially, but the velocity profile, whatever the velocity profile is here, the same velocity profile only here also, the same velocity profile only here also, same velocity profile only here also. The velocity profile should not vary with longitudinal direction. Velocity profile is going to vary only radially. So that is the first condition for fully developed flow. So what is that? Velocity profile should not vary in longitudinal direction. Velocity profile should be varying only with respect to radius. So how it is varying, we will see. Okay, so we have a separate study of that. We will do that, how it is varying. But you need to understand that it is varying only radially. It is not varying longitudinally. Next condition. So what is the next condition? Let me just elaborate it properly. Okay, so let me represent pressure in y-axis, and let me represent this x is nothing but length of the pipe. Okay, this is length of pipe. So this is the place where we are differentiating entrance region and fully developed flow, right? So one thing about pressure with respect to x. So what is that? We just now seen before Darcy-Weisbach equation, we seen that pressure is going to get dropped. If it is an uniform cross section pipe, there is going to be decrease in the pressure. Okay, so pressure drop will be there, so pressure gradient will be negative. Okay, pressure gradient is nothing but dB by dx, that will be negative. That is fine. So there is going to be drop in the pressure. There is going to be drop in the pressure, but in fully developed region, okay, in fully developed region, pressure is going to get dropped, that is correct, but pressure gradient has to be constant. The drop in pressure has to be constant. What actually it means, let me just plot it. Okay, so if I plot it, you will understand. So this is pressure. So in entrance length, the pressure can vary in whatever manner it wants. So it is not going to increase. Ultimately, it's not going to increase. It's going to decrease only. It's going to decrease only. There is no possibility for increase. It's going to decrease only. But that can happen in a curved manner. Okay, there is no necessary that it has to be a straight line. Here, dou p by dou x is not constant. See, dou p by dou x is nothing but what? So it is a slope, right? Like if you already attended that mathematics class, you will know that dy by dx is slope. In this case, y is p, y is pressure, x is length of the pipe. So dy by dx is slope. Slope has to be constant in fully developed flow. So when will be slope constant? For this, you can just go back and see our slope video, which has been already discussed in basics. Okay, so when will be slope concept? Slope will be constant if it is a straight line, okay, linear straight line. And I know that the pressure is going to decrease, so pressure has to decrease. See, here also you could see that pressure is decreasing, but the slopes are not constant. You could see here I am having a slope like this. If I take a point here, I will get a tangent like this. If I take a point here, I will get a tangent like this. So slopes are not constant, but once it reaches, okay, once it reaches fully developed flow, okay, so once it reaches fully developed flow, the slope has to be constant. So that is the most important thing to note. You could see here the slope value, dou p by dou x value is constant. See, you will understand this in a more better way if you understand slope. So just try to go and see the slope properly. See, pressure has to decrease. The pressure is decreasing. Pressure is dropping. You could see y-axis it is decreasing. But dou p by dou x is not constant in entrance length or in entrance region. And in fully developed region, dou p by dou x is constant, which means the slope of pressure or pressure gradient has to be constant. Okay. Right. So now finally, what is the conclusion which I need to give for fully developed flow? First conclusion is velocity is not varying. Velocity profile is not varying in horizontal direction. Velocity is varying only in radial direction. Okay. Second conclusion, pressure gradient in fully developed flow has to be constant. So pressure gradient need not be constant in entrance length. see, entrance length, entrance region is complete region. Entrance length is nothing but this distance. Okay, from the starting point until this distance is entrance length. Measurement of length, if you measure it, if you measure the length of this pipe, that is entrance length. Okay, from here to here. And what I was saying, right now, for a fully developed flow, u is not a function of x, u is only function of fr, as I said, right? If u is not a function of x, can I conclude one more thing? What is that? See, this is 0, okay, this is u max, this is 0, this is u max, and similarly each and every point there will be velocity, and those velocities are not going to vary in horizontal direction, in longitudinal direction. If it's not going to vary in longitudinal direction, then average velocity will also be constant, right, along longitudinal direction. This we already know, because it is a uniform diameter pipe, so average velocity has to constant, because area is constant, so average velocity has to be constant to compensate our discharge equation. A1 V1 should be equal to A2 V2 continuity equation. But anyways, we can say from this also, since u is 0 here, u is maximum here, so that along longitudinal direction there is no change. This distance will be equal to this distance will be equal to this maximum distance will be equal to maximum distance. So everywhere that will be same. Only radially it is varying from maximum to 0. So average velocity at each and every section will be same. So I can say that u average is not a function of x, which we already know. Average velocity is not going to vary because it is an uniform diameter pipe. So area remains same, velocity has to remain same for satisfying continuity equation, right? So it's a very good concept, as I said, okay, fully developed flow. So the condition you need to remember, and I hope that it makes more clear, like what is a clear cut concept, a crystal clear concept of fully developed flow.